Welcome to the HasMotion YouTube channel. In this video, we will be going through a tutorial showing how to analyze shooting arm mechanics in basketball for free throw shooting and use statistical analysis methods in SIFT to identify patterns. This tutorial uses a case study of n equals 1, whereas most existing research looks at larger groups. Using one individual's data can help identify inter-subject variability between shot types, as opposed to looking at inter-subject variability in form. In this tutorial, we hope to identify any significant differences in shooting arm mechanics between makes, left misses, and right misses. We'll do this using a combination of PCA, SPM, and K-means in SIFT. We'll use data from an open source dataset made public by the MLSE. This dataset includes markerless motion capture data for one person shooting 125 free throws over a span of 2 to 3 hours. It also includes important information like the coordinate system that can be seen on the screen right now. We will reference both the rim and court coordinate systems later on. Once you've downloaded the data from the P001 folder linked in the description below through the wiki, make sure to take note of its location and folder path. This will be important when we load the data in the next step. Now that we have an understanding of the data and it has been downloaded, we can start building the pipeline to process the data. Start by creating a folder on your computer called Free Throw Project. Within this folder, create a subfolder named V3D Pipelines. You can also add your free throw data to this folder to keep things simple. To start building our pipeline in Visual 3D, navigate to the Pipeline Workshop. First, we will use the set pipeline parameter folder path command to call on the folder we just created. This command can be found within the Pipeline Control section of the Pipeline Workshop. Once you have your command open, start by changing the parameter name to call script path. Next, we'll change the parameter value to the V3D Pipelines folder that we just created. This folder will contain all of the pipelines we create as well as the free throw data that we need. Next, we'll select the Set Pipeline Parameter to List of Files command. This command can be used to select all the files within a given folder. Navigate to the folder containing your free throw data and make note of the location. Copy the address as we'll use this to edit the command. Make sure the parameter name is set to Files and change the folder location to the folder containing all of your free throw data. We're going to change the file mask to .json as all of the files contained within the free throw folder are .json files. Before you run this section, create a second folder named P0001 processed within your computer's directory in the free throw data folder. This folder will contain all of the processed data once we execute our pipeline. Having a separate folder for our processed data allows us to keep the original data intact and simply focus on the processed data when we want to perform statistical analysis. With the commands made to load files into the pipeline and save them in a new folder, the next step is to run the for loop that creates .cmz files. To create a loop, add the command for each, followed by the command end for each, which closes the loop. The iteration parameter name should be set to index for both. Additionally, we'll change the iteration parameter count name to count and items to files. Once you've defined your for each command, we can build our end for each command with the same parameter name set. Within the for loop we just created, we will add 3 commands to create a new file, open it, and then save the file to a given folder. The file new command will be used to create a new file, while the file open command will be used to open the file that we created, and then finally the file save as command will be used to save data to that file we just made. Within the file open command, select all of the parameters other than file name and remove them as they're not relevant to this command. Change the file name to index and save the command. Navigate to your folder containing the process data and make note of the address. We'll change the name and folder within File Save As to the direction of this folder so that the new data we've just created is saved to the processed folder. Within the File Save As command, we'll change the name to trial and count and then change the folder to the address of our process data folder that we just saved. Ensure that File New, File Open, and File Save As are properly formatted within the for loop like so. This will make sure that the commands run properly. Now we can save this first part of our pipeline to the v3d pipelines folder that we created with the name 0_call_scripts. This will be the first of multiple pipelines that we create to process our data. Now that we've saved this section of our pipeline, we can clear the pipeline workshop and begin working on the next section. The next section of this pipeline will create commands to assign tags to each free throw attempt based on its outcome using the information provided in the MLSE dataset. In order to support the following steps in this tutorial, this step in the pipeline will tag each shot as made or missed and determine whether errant shots were missed right or left of the intended time. To start, we'll add the assign tags to files command, and this will be used to tag shots whether they were made or missed. First, change motion file names to all files and direct the query to the made shots within the MLSE results. Change the tag to made to highlight that these shots were made. Next, we'll do the same for the missed shots. However, we'll change it to missed within the query and change the tag to missed to make sure that these shots are recorded as having missed the net. Next, we'll use the same command 2 more times to identify shots were missed left or right. We'll define left shots as shots that were more than 3 inches left of the center of the hoop, and we'll define shots that were missed to the right as shots that were more than 3 inches right of the center of the hoop. Sorting these shots into groups that were missed left or right, as well as made versus missed, will help us identify more distinct differences between joint characteristics later on when we perform statistical analysis in SIFT. If we only sorted the shots into made and missed, there may be more significant overlap between the groups, as the missed shots will cover a wider spectrum versus just being on the left and right side of the hoop. Now that we've assigned the appropriate tags to shot groups according to their results, we can save this pipeline as one_assign_tags in your pipeline folder and clear the main pipeline. The next part of our pipeline will consist of separating the free throw motion into phases by adding event tags to certain positions throughout the movement. This helps to highlight how signals change at different points during the free throw and will help us identify phases in which variance between shots is the most significant. We'll use the position of the center of gravity of the right hand as the closest approximation of the position of the ball to define different event moments. Start by adding event global minimum and event global maximum. We'll use these commands to define the start and end of the shot phase by defining the lowest and highest position of the center of gravity of the right hand. This will identify how the ball moves from the lowest point of the shot to the highest point of the shot prior to the release. We'll use the center of gravity position in the Z direction, which is the vertical axis, to track the position of the right hand throughout the shot. This is the closest we could get to tracking the position of the ball, as the ball didn't actually have trackers on it in the marker set, but because the right hand is connected to the ball, it gives us a close approximation. The typical free throw motion can be separated into two distinct phases between start and end, not dissimilar from a counter jump. There's a loading phase and a release phase. The loading phase consists of storing energy in the knee, wrist, and elbow joints through simultaneous knee flexion, elbow flexion, and wrist extension. The release phase sees the straightening of these joints to release the ball. We'll then again use the event global minimum command to find the minimum vertical position at the distal end of the right thigh segment. By setting the event sequence to start plus end, we'll only take the global minimum within these events. We're using this position of the distal end of the right thigh to approximate the knee position, and this gives us the best idea of separating that loading phase between the launch phase. Now that we've defined the key events and shot phases, we can save this pipeline as 2_define_events.v3s within that pipeline folder and go back and clear the main pipeline so we can build our final pipeline. The fourth and final section of our pipeline will consist of identifying joint angles and joint angular velocities for the upper arm across the shooting motion. These angles and angular velocities will be used to perform analysis and identify distinct differences between the different shot types that we've assigned earlier in this pipeline. We'll add the compute model-based data command 6 times, as we'll be identifying the right wrist angle, right elbow angle, right shoulder angle, right wrist angular velocity, right elbow angular velocity, and right shoulder angular velocity. The right wrist angle will be defined between the right hand and right forearm, while the right elbow angle will be defined between the right forearm and right arm, and the right shoulder angle will be defined between the right arm and the right thorax. Here we're defining the right elbow angle as an angle between the right hand segment and the right forearm segment as a joint angle. Next, we'll define the wrist angle between the hand and forearm segments for the right arm. To view a more detailed description of these segments and reference segments used to define the angles and angular velocities, visit the wiki link in the description. Additionally, through the wiki, you can find a completed version of this pipeline for all 4 pipeline commands that can be downloaded and loaded into Visual 3D. Downloading the completed pipeline from the wiki will allow you to go straight to processing the data and skip the steps detailed in this video, though we do recommend following along the video so you have a greater understanding of how the pipeline is defined and the steps that were used. If you do run into any errors while running your pipeline, downloading the pre-made pipeline can be a very effective way to troubleshoot and compare the pipeline you've made to the correct one. Next, we'll define the right shoulder angle. Each joint angle has an associated X, Y, and Z angle to it. For the shoulder, this indicates flexion extension, abduction, adduction, and internal external rotation. Here we'll define the shoulder as the angle between the right upper arm and the right thorax. Now that we're wrapping up computing the joint angles, we'll move on to computing the joint angular velocities for each of the same joints. These angular velocities will be defined by the same segments and reference segments, but have an additional resolution coordinate system for each of them. The right wrist angular velocity will have the additional right forearm as the resolution coordinate system. The right elbow angular velocity will have the right arm as the resolution coordinate system, and the right shoulder angular velocity will have the right thorax as the resolution coordinate system. Make sure to change the command function from joint angle to joint velocity for each of these commands. For the right shoulder angular velocity, we'll look at an example of doing it using the dialog box instead of editing this text. Here we'll select the data name, select joint velocity, and then for our segment, select the right arm and relative to the right thorax, and the resolution coordinate system as the right thorax. If you prefer to edit as text, the right shoulder angular velocity can be defined like so. Now that we've computed all of the necessary joint angles and relevant joint angular velocities, we can save this pipeline as 3_compute_model_based_data to the same folder and clear the main pipeline. Finally, we can go back to our original pipeline 0_call_scripts.v3s. Inside this loop, we're going to make some necessary modifications prior to executing the full pipeline. First, we'll add the select active file command. This command is run first to select the file to be updated. In this case, we'll be applying the pipeline to all of the files. Next, we'll add the call script command 3 times. This command will call our scripts that have just been written. Simply input the name of your script, followed by the path to the pipeline folder where the scripts are saved. Remember that we created call script path as a pipeline path name in the beginning of the tutorial. We'll reference that here. All of the commands and pipelines required to effectively process our data for our purposes are now included in the pipelines that we built. You can now click Execute Pipeline to process the data, and we'll navigate to our results within the Visual 3D page. Now that our completed pipeline has been executed, we can look at an animation of a free throw attempt and view a joint angle. Select the Signals and Events tabs and a shooting trial at the top of your window. On the left side of your screen, click on the right shoulder angle in the link model based folder and graph the X, Y, and Z angles. Notice how the events we defined for start, launch phase, and end of the shot are marked on the graph. Now that we've completed our pipeline and processed the data, we can move on to using SIFT to visualize and analyze the data using different statistical methods, including principal component analysis, k-means, and statistical parametric mapping. To start, from the home screen in SIFT, select the Load Library button and navigate to the folder containing your processed data. Select the appropriate P0001 processed folder from your V3D Pipelines folder and load it into SIFT. You should now be able to see that all 125 free throw trials have been loaded successfully into SIFT. Try selecting one. You'll be able to see that the appropriate groups and tags have been assigned to each. On the right, you can visualize one of these trials using the animator. Now we'll move on to building the necessary queries to sort this data into appropriate groups according to joint angles and shot results. This can be done step-by-step manually, or the completed query file with all 27 queries can be downloaded from the wiki tutorial page. We will create 3 queries for makes, left misses, and right misses for each of the 3 directions for all 3 shooting arm joints, the wrist, elbow, and shoulder. This totals 27 queries. Navigate to the query builder and add a new query named wrist angle x made. Within this query, add a condition named right x. In the Signals tab, select No Subject, and then for folder type, select Link Model Based, Original Folder, and make sure to select the right wrist angle under signal name with the X direction selected for the component. Next, in the Events tab, we'll select Start, Launch Phase, and End to make sure that the signal is tracked over the entire course of the shooting motion. Finally, we'll move to the Refinements tab and select Made to make sure that the signal is refined to only include made shots, not missed to the left or to the right. Now that all the necessary conditions have been applied, we can save this query and move on to making a new one for wrist angle x missed shots. First, we'll make one for the missed shots to the left. Next, we'll make one for the missed shots to the right and apply the appropriate conditions to define each of these groups. We'll use the same signals and events for each, but make sure that in the Refinement tab, we have missed and left selected for misses to the left, and then missed and right selected for misses to the right. Make sure to use the AND logic to make sure that both of these conditions are applied. Repeat these steps for makes and misses for all of the remaining join angles, or feel free to download the completed queries from the wiki link in the description. This will make the process a lot faster. Now that all 27 of our queries have been made for each join angle, we can calculate all queries and see how this sorts our data. Click the Calculate All Queries button and navigate to the Explore tab within your SIFT application. All of the workspaces created by our queries contain the data stored within each CMZ file we saved, sorted into groups according to shot result and the selected join angle. Each trace shows a visualization of a join angle across an individual C3D file. To best visualize the differences between makes and left and right misses, it makes the most sense to compare these groups for just one join angle at a time using workspace mean. This allows us to see potential trends across left and right misses within each join angle and direction. First, in the Explore tab, select 3 groups that you wish to compare. For this tutorial, we'll start with the wrist angle X made, wrist angle X missed left, and wrist angle X missed right. Select all workspaces on the left, as well as plot group mean and plot group dispersion. Your graph should look similar to what is shown on the screen. Compare the rest of the joint groups and see what stands out. To look for and identify potential outliers, click Plot All Traces. If you see a plot that looks unnatural or different from the rest of them, you can highlight it and exclude it from the traces. We won't be doing this for this trial, but it's a useful tool going forward. To account for any phase variation across the shots, we'll perform curve registration on each of these traces. Since the most variability in joint angles occurs in the X direction, which is flexion and extension, we're only going to show here an example of curve registration on the X curves. Select the groups you wish to register on the left side of your screen and click Register Curves. We'll define the event sequence as start, launch phase, and end. Click Event Sequence and register your curves. Repeat this process for the remaining curves that you wish to register, including all of the groups in the X direction. You should now be able to see all of your registered groups at the bottom of the groups list. Visualize them and see how they compare to the original groups. Now that our data has been sorted and our curves have been registered, we can move on to performing statistical analysis using 3 different methods to identify the relationships between shot results and joint angle variance. We'll start by using principal component analysis. PCA is a useful tool for data visualization and identifying complexity and variation between data groups. Start by selecting the groups on the left that you wish to compare. We'll start with the left and right misses for the right wrist in the X direction. Navigate to the PCA button on the top toolbar. This will open a dialog box. Name this PCA right X misses and set the number of PCs to 6. The number of PCs will change for each group. We want the minimum number of PCs necessary to explain 90% variance. For this example, 7 PCs reach this threshold. Repeat these steps for misses in the X direction for the elbow and shoulder joints. Adjust the number of PCs for each such that 90% or more of the variance is explained. This should be achieved by 6 PCs for the elbow and 5 PCs for the shoulder. Now, by exploring the different tabs at the bottom of your screen, you should be able to see several charts associated with your PCA, like variance explained and group scores. To learn more about what these mean and how PCA works, click the link in the description to access the wiki tutorial. PCA works by reducing the number of variables in a dataset while retaining the most important patterns or relationships between the variables. PCA constructs new variables, or PCs, as linear combinations of the original variables. These PCs are ordered by the amount of variance they capture from the data, with PC number 1 capturing the most variance and PC number 5 or 6 capturing the least variance. We can see this in the variance explained plot produced by the PCA. A higher number of PCs required to meet our 90% threshold indicates more complexity in the variance within that test. Now that you've completed the PCA for misses for all 3 joint angles, Navigate through the tabs at the bottom to look at different results like the loading vector, workspace scores, group scores, extreme plot, and the PC reconstruction. Once PCA has been successfully performed on select groups, we can use k-means testing on the results. K-means testing uses an unsupervised algorithm to create clusters of data with similar characteristics. This should help us identify whether or not shots can be clearly grouped according to outcome based on each joint angle. To perform k-means on our results, navigate to the Outlier Detection using PCA button on the top toolbar. Select k-means from the drop-down menu. This will generate a dialog box. For each group, select 2 clusters and 5 maximum iterations. Check the determined number of PCs using variance explained and set the variance to 90%. Also check the switch display style to by cluster box. Going through the cluster information for our k-means results provides more information on how our groups are clustered. Run k-means for the misses for each joint angle and navigate to the Workspace Scores tab for each. Looking at this, as well as the cluster information box, gives us key information on which shots are collected in which cluster groups. If we see that right misses and left misses are separated by cluster, this gives us a clear indication of a pattern within the misses for each joint angle. Take some time here to review the clusters that were created and see if you can identify a clear trend across the clusters. For this one, we see a clear trend of one cluster being on the bottom right and the other cluster being more up and to the left, although there is some overlap between. Clusters that are more clearly defined generally mean more definitive differences between the groups. The final analysis method we will use is called SPM, or Statistical Parametric Mapping. SPM is a statistical analysis method originally used in neuroscience that can be useful in determining the presence of statistically significant differences across the entire waveform. Here we will use it to compare left and right misses for each of our arm joints in order to determine the factors that perhaps lead to a missed shot. The importance of registering our curves comes into play here because statistical parametric mapping performs analysis comparing the signal over an entire waveform. If we didn't register our curves, we would run the risk of artificial variance because our waveforms would not be aligned properly. To build the SPM, first select the 2 groups you wish to compare from the groups list on the left. Next, navigate to the SPM button on the toolbar. Before building our SPM, we must first build a generalized linear model, or GLM, which helps to quantify the variance between parameters. For the wrist, select the group shown on the screen. We'll use a 2-sample t-test for each joint. Now that we've built and can see our GLM, we can use it to compute the SPM. Select the Statistics tab at the bottom of your screen and click Compute SPM. Select wrist X left and right misses as your 2 groups, a threshold of 0.05, and check the 2-tailed box. Repeat these steps for the shoulder and elbow misses. In the SPMs that are produced, the areas in which the line crosses the threshold and is highlighted in blue indicate areas of statistically significant differences between 2 missed groups and between joint angles. Now that all of the necessary statistical analysis has been performed, we can move on to interpreting results and drawing conclusions. Once the waveforms for makes, left misses, and right misses have been visualized for all 27 queries, we can see subtle differences between the results for each joint angle based on the shot result. The most significant differences we saw were in the flexion-extension patterns for each joint. As such, we performed further analytical testing on the left versus right misses and how they were impacted by shoulder, elbow, and wrist movement in the X direction. The null hypothesis states that the joint movement would be consistent across all shots. This is rejected by our SPM testing, which shows small but statistically significant differences in shoulder, elbow, and wrist flexion for left and right misses during the release phase of the shooting motion. These differences were first identified using visual inspection of the signal time plots shown on the screen and confirmed using K-clusters and statistical parametric mapping. This research builds on existing biomechanics work done to optimize free throw mechanics, although prior research focuses mainly on lower body mechanics and release height. Further analysis on a greater field of subjects could be used to identify if these patterns are consistent across different individuals and skill levels. 2 additional optional steps are included in the wiki link in the description, with instructions to generate signal plots and automate the command line. The signal plots can be useful to compare the signals for makes, left misses, and right misses at different joint angles instead of just in relation to time. The instructions to make the necessary pipeline modifications and build the plots in SIFT can be found near the bottom of the wiki page. Command line automation can be very useful if you're dealing with several subjects. It wasn't necessary for this tutorial as we were only processing data for one subject, but for a larger trial with tens or hundreds of subjects, it would significantly streamline the process. Be sure to save your SIFT workspace as an i3D and export any of the plots as necessary. Instructions on how to do so can be found in the tutorial list on the SIFT wiki. Thanks for watching. We hope you were able to learn something new about free throw mechanics and how to use the tools in Visual 3D and SIFT. For more helpful resources and tutorials, check out our YouTube channel or our wiki that's linked in the description.